finally that I think is working now. So okay, let me start it again. So this is just kind of like get you guys interested. So again, okay, take a little bit time to run this, but okay. So I don't know. Like again, the same questions. I'm not sure. Toaster can see this earlier, or like and oops, this time it screw up. So anyone know this game? Like, what's the name of this? Yes, okay. I thought you guys may be too young for that. So by the end of this course, you don't know how to program this game, but you know how you can program AI like this. This player here, I don't know, like how do you call that? Like this whatever, this yellow thing. So it's kind of like you see, like when I first started that, I trained it a little bit, like for a while. Then afterward, now it's testing it. It's playing it pretty perfectly. But in the sense, you see that like it doesn't understand. Like it's just trying to avoid these two ghosts here, and it didn't realize like the use of this thing. Like it's still trying to avoid this. What do you call this? Like bigger beans. They're trying to like I guess it's still trying to avoid it afterward. But anyway, like but you can see like almost kind of get it perfectly. Like finish eating all the beans like without getting caught. And so I guess there's a score here at the back, like you can see. I guess it failed one time, like Pacman died, like the score like have the cost like it's like 68, and afterwards like it's all like of course as you know, like probably you can guess that we probably like the rest of everything we study like in this class, there's some objective function at the back end that trying to optimize. So the first time it failed, therefore the cost it has like pretty low score there, like but afterward it's all pretty high. Oops. Okay, still managed to avoid those. And so oops. Yeah, I mean it's pretty amazing. I there's no way I can control like this. So and yeah, I guess that's enough. So I guess I will just get to the actual materials there. So as I mentioned, we are going to talk about like reinforcement learning, or a little bit more like actually more precisely some deep reinforcement learning. But mostly we'll talk about spend quite a bit of time on reinforcement learning. Then like we'll see like the spin like from reinforcement learning to deep reinforcement learning. So these slides actually I kind of stole from like a Berkeley course, an AI course, and modified quite a bit. So basically, like reinforcement learning, I guess by this time you know pretty much supervised and unsupervised learning, right? So reinforcement learning, you can more or less think of like the intermediate of that two. So for supervised, you have the teacher there like kind of explain like exactly what you're supposed to do, like kind of like holding your hand more or less. And for unsupervised learning, there's no key objective there. And this is kind of like reinforcement learning it's kind of in the intermediate. So for example, you think of like trying to teach a car to drive yourself. So you won't exactly telling like, okay, now you should turn like so many degrees and so on. It will only tell you like whether you do well or not well, whether you're keeping on the lane, or like you hit someone or you kill someone or something like that, or you kill yourself. And also like other example, for example, like we just showed the game AI, like control whatever, like players, and also like robots, also like robotic control that lots of use for reinforcement learning. So actually, like in the past, for example, like we have like this robotic control is like mostly using classical control method, right? But since I guess last decade or so, like many of these techniques has been replaced by reinforcement learning. So and the model is quite simple. Basically, you think of like you have some reward. I mean, you basically you have an environment first, and you have some agent. You consider you need to teach your agent, and according to the environment that you have, what's the current state, right? The current state, you have the state information now at this moment at time t, and then like also according to what action you have taken in the past, like you have the current reward. So what you want to teach the agent is like given the current state and the current reward, or like actually not just current reward, but like the reward information up to now. We want to teach him to take the appropriate action, to introduce the appropriate action. So this is the model basically. So what we're going to talk about today is a Markov decision process. It is basically like a non-deterministic. Okay, actually, actually, I said something wrong. Okay, we'll talk about Markov decision process, and then like it is in the same Markov decision process. Like the model is kind of well defined, so you know exactly what the model is like, and then we'll extend to, and that is not actually, strictly speaking, not even strictly speaking, it's not reinforcement learning yet, but then we'll kind of extend that to reinforcement learning. We'll introduce Q-learning. Basically, like we don't know exactly what the environment, the model is like. We need to learn the environment and learn how the models work. And then we will further extend to like approximate Q-learning and deep Q-learning. So to start with, we just have consider a very simple example that we have a so-called grid world. So we have an agent. It's like a tiny kind of like robot here. It will just like walk along this grid world. It can walk one step at a time, explore this grid world. And there's some trap here, like if we drop here, it will have like some penalty, or like there's some bonus here, like if it go here, reach here, it will avoid something. So the goal is like how we are able to control this robot, we reach the goal. And further, like typically we'll assume that like the model is stochastic instead of like deterministic. What I mean is that like if we are giving some instruction to the robot, so for example, I ask the robots to move forward, it's not 100% like, I mean 100, with probability of 1 that it will actually move forward. You can consider maybe in the actual world, like maybe there's maybe some dirt in the wheel, so when it's trying to move forward, maybe it just drifted a little bit to the left or something. Or like you just think of Womber, if you see Womber like how it actioned before, like it doesn't always like move to the way it's supposed to move, I would say. So let's give this slight probability. Let's say like if I say like 80% you're going to ask it to move forward, it will just 80% of the time will move forward actually, and then maybe 10% will move left, and then 10% will move right, so on. And we also assume that it cannot hit a wall. I basically like if it moves to the wall, like it just cannot hit it. Like it will just cannot move that direction, something like that. So okay, just a very simple example. Again, like how given this model, like how we can maximize the award here. So as I mentioned, like instead of this deterministic model, we have this like stochastic model here. Like given one action like that, we have like several different possible outcomes. So now let's give a kind of like more precise definition of the Markov decision process. So it's composed of, as I mentioned, that we have the reinforcement learning model, that we have the environment that's kind of specify the current state, and then the agent specifies some action, right? So therefore, like just as in the reinforcement learning model, like in this Markov decision process, we also have the state and action. So state is basically, in this grid wall example, basically like where is the robot is the state, right? So at the particular location, it will be the state of the robot, and then like the action will be like just instruct like where it's supposed to move. Then there will be some transition function given the current state and the current action. So this TSA S pi here will specify what's the probability, more precisely transition probability from state S to S pi when we ask the robot to take the action A. And then given that, like we will also have the reward function, like it's like reward S, A, and S pi. Actually, most of the time, like we can simplify that to just RS. So typically, the reward will only depends on the current state you are at. So we can simplify it RS. Then of course we have the start state, and we can have like terminal state. For example, here, if we reach the goal, then we'll just stop. Like that would be the terminal state. Or like if we reach the trap, then it will also stop. So MDP is basically just a stochastic search problem, a non-deterministic search problem. So what we want to have eventually is basically a policy for this robot. So a policy meaning that like given the current state what the action, that will be a unique action given instructed to the robot. So that we call it the policy. So the policy therefore is basically just a mapping from the state to the action to a action. And also like let's say we just call this pi star here will be the optimum policy. So that we basically want to look for this optimum policy. And also like typically like we have, for example, like here for the reward, as we show early in the early example, like we draw the map here with this -1 and +1 like as the trap and also the award there. And besides this actual reward there, typically we can also introduce some instantaneous reward. So most of the time it's just trying to, in the sense that this instantaneous reward can control like how urgent that you want the robot to get to the destination. For example, like if I have a reward like for each state is except these two states is -0.01, that is not too kind of like give a very urgent, a very strict urgency to that robot, then it probably go pretty slowly, trying to avoid the trap as much as possible. So therefore, like if here it's just trying to move here, right? It try to hit the wall because it's just trying to avoid this thing, right? It can go only this way and this way. So, but as we increase this kind of like intermediate reward there, or like decrease the intermediate reward there, make it more negative, then you see that like it didn't try to avoid the wall anymore. It just tried to go this way, like try to go faster. And here, like as you increase that, change the policy a bit. If you change it like really high, or like really negative for this intermediate reward, immediate reward, then like it's just trying to jump off as soon as possible, right? Jump off to one of the destination. So this is all very straightforward, like intuitive. So what we the way to tackle this problem, like to look for this policy, is going for a tree search. Basically, we're trying to build a MDP like this Markov decision process search tree, and then try to go through the tree and try to, it kind of like intuitively it would be like just go through the tree and try to look for the optimum, right? So of course in practice you may not need to, but yeah, you don't really need to kind of expand the entire tree. So here just give an example, like if I start with some state here S, and then I give some action, then there's some several possibility that it will, wait a sec, okay, if I give an action here, I will reach here, I say here, and then for the next state, because it's not deterministic, right, so it has several possibilities to go to other states here, but let's say it reach to this S pi here, and again, like the probability from here, like this SA to S pi would be like TSA S pi, and the resulting reward is RSA S pi. Utility. So, okay, I guess I will probably just skip this one. Okay, for discounting, it's very similar to the immediate rewards that we mentioned. Discounting is another way to introduce some kind of urgency, or like another. It's also have like something like some other uses you can see. Especially it's kind of like you can interpret that like probably more intuitively, because you think of reward like think of like each time step is the actual time you spend. So, for example, like you need 1 day to move 1 step, let's say. Then, if you think of like the reward is actually some kind of like monetary reward, then you can think of like whether you want to get the money now or you want to get the money like tomorrow, right? So, of course, you get the money tomorrow, like it's less attractive, right? And how much less attractive it depends on the current interest rate, right? So, therefore, the discount rate is kind of like if you think of the monetary or the economic wise. Interpretation would be like just linked to your interest rate. So in general, like so you can think of like something like right now, like you say like it worth like 100% of it, and then in the next day, next step, it worth like gamma times like the current worth there, and typically gamma is less than 1, and then if 2 steps will be gamma squared and so on. So doing discounts, as I mentioned, is a way to reflect like this, whether you want this urgency like to get to the destination, and also like it kind of help out in the sense that if you think of like if each step is going to give you some reward, and let's say there's no destination for the model. So that's not necessary you have a destination, right? Then in general, the sum can be like infinite sum, right? Even if like each of the reward is like finite. So if you have the discount, this also like avoid this infinite sum problem. So okay, anyway, that's as I mentioned, you have this infinite utility, but if you have the discounts, then we'll avoid that. So so far we have this, and it's quite, I guess it's quite clear, right? The model is quite clear. It's relatively simple, this Markov decision process. Now we get into like how to solve this Markov decision process here. So maybe I should just give this, let's say, this is an illustration of the game we showed earlier, and let's say each of these triangle here and the number here is indicating, for example, like this number is saying that like if I am at this state and taking this action, then my expected like okay, first of all, if I'm at this state, like at this state here, if I take this action, it doesn't necessary that I will move to here, right? As I mentioned, I may also move to here and also move to here, right? But I will have like high probability to move to here, and I can also compute the expected reward, right? because I have like, if I move to here, I have some reward. If I have moved to here, I have some other reward. Move to here, some other reward. I can do a weighted sum of them, and let's say this will be the weighted sum. So, am I clear? So, I mean, like if I stay here, I mean, if I take action in this direction, my expected reward will be like this. And if I, at this day, I might take this action here, my expected reward is like 0.4. Yeah, if I, oops. Yeah. So, okay. And from here, I think it's pretty clear, right? So, I'm here, like, what action should I take? Do you see what this number doing again? Like, here's what this number is doing. So is that Unsama? Like I saw you nodding. so you get the what I can't hear you. Like you are mute, I think. Yeah. Yes. So yeah, I didn't mute you, but I think like you guys are mute or somehow like there's no sound from your end. Okay, yeah, I can hear something now. Yeah, I can hear. Yeah, I can hear something now. So again, like the question is like, if I'm here, what action should I take? Like given this figure here. Up. Yes, it's right. Wait. Up, right? And how about here? Yes. How about here? Yes. So, I mean, like, as I mentioned, so it's obvious, right? If I have, this is basically the, at each of the state, and this is the expected score, like taking like action from each of the direction. Of course, I will take the maximum one, right? So, and that's basically, yeah, obvious, right? So, therefore, if I know the expected, I can hear you now, actually. Wait, I can hear you earlier on, but like not. Oh, it was. So can you hear me? Like Okay, yeah. But I can hear you actually. I think I can hear you. Say something. I can hear some noise, but I cannot. Okay, I can hear you. Yeah. Yes, but earlier I cannot. I think like somehow you click something or something. Yeah. So
We have been speaking to you, but you were not responding, so we thought you don't hear us.
yes, earlier I think. Yeah.
Oh, okay.
Yes. So then the remaining question is like how we can find this, right? Given the current state and current action, how do we find the expected reward there? The expected reward we call Q. So as you can see, like why we have like Q-Learning later on is trying to learn this Q function there. And this is like another example that like even we can also like not even know the action if we know the value of each of the state. The value is basically like at each of the state what's the expected reward at that particular state, given you take the optimum action. So as you can see, it can be drawn just from this figure here, right? For example, if I am stay here, if I take the best action, then the value of this state will be, so therefore the best action is 0.57, right? So therefore the value of this state is just 0.57, and this guy, the value of the state is just 0.85, and so on. And even if I'm not given this like Q function, like QSA, just giving the value of the state, apparently I can also like conclude like where I should go, right? I should just go along the direction that I will increase my kind of like expected reward, right? So for example, here, if I move to here, I will have a high expected reward. Then I move to here, then probably I should move in this direction, something like move in the up direction. And so again, the question is like finding this Q function or the V function there. As I mentioned, like the V is basically just the Q taking the optimum action, right? So therefore it's like maximum over all the action there. And then like now given the and also like Q itself is just the expected reward over all the possible state, right? So because as I mentioned, if I initially in state S take some action A, I can get into like different state S pi, right? So I need to do an expected sum over all the different states pi there. And this is just basically the conditional probability, transition probability to do new state S pi. And then the reward getting to S pi will be simply like this, right? Because I will have a reward from S to S pi, that is the immediate reward there. But then like, what after I reach S pi, now I'm at S pi in the next day, right? So I will have like the expected reward and S pi there. Like I should add also the expected reward for S pi there. But I should discount that like for gamma because it's one step later on, right? So therefore, like if I start from S, next time I reach S pi, then the reward will be simply the immediate reward added the delay satisfaction like for like V S pi there, right? So therefore like we have this so-called Bellman equations. So therefore like basically what we have is just trying to Vs will be just like maximizing this thing here, right? So we have this Bellman equation. And now you look at this Bellman equation. We have Vs here and Vs here. A very simple way of solving this will be simply doing an iteration, right? Basically, if I start with some approximation of V here, I can just update this new V as like the previous V like on the left-hand side expression, right? So then like we can keep updating that like to just get a better approximation of V. So and we can just keep repeating until we converge. So the complexity is a little bit high, but it kind of works. We will explain like we'll kind of like explain a alternative that if you don't want to, if you think this kind of like complexity is too high, that's another kind of, yeah, we'll talk about that later on. So but anyway, this is an example. Like we can start with like assuming all the state have like value 0, and then like we just keep iterating, right? And then we will slowly propagate all these values like to as I mentioned, like after 100 iteration, we basically get converge and like we get the values as we showed earlier on. So this is a kind of summary of what we just mentioned, and it's basically like this value iteration is just a fixed point solution, like kind of like in numerical method to compute a solution. And as I mentioned, you may consider value iteration is too expensive. The problem is that if you look at the value iteration, like each time you need to consider all the possibility, right? For example, given the state S and consider one action here, we still need to consider all the possibility like S pi here. So okay. Actually, I'm sorry, I made a mistake here. I should talk about this A here instead of. So this I cannot control here, but here like for the original value iteration algorithm, we always pick the best action there, right? So we need to like consider like all the possible action and look for the best one here. So one alternative is like, okay, let's fix the policy first. Like we just assume like, okay, at the current moment, the best policy is like some pi s here. Just stick with that. So in that case, I will just shrink down this action selection quite a bit, right? So if there's n actions here, we just need to pick one here, just to expand the tree. So if we use that to approximate the value, so basically we have assuming that like given this fixed policy, we want to know like what's the value of the current state. So then more or less we'll have a very similar update, right? So instead of having this fixed point update have maximized over A here, we don't have this maximize over A here anymore. So we just have this one here. And know that like this guy, of course, we can also do iteration again, like just with this replacing with this guy here on the left hand side. But at the same time, if you look at this here, like since I don't have this mass operation anymore, this is actually just a linear equation. We can even move this guy on the left hand side or something, and we can. Actually, I think I keep saying like left hand side, like this is right hand side. I'm sorry about that. Yeah, yeah. I can move this like to the left hand side and then like just solve it as a linear equation. So, and this is an example. Let's say we start with like policy always just go right, and like, this policy always move forward, and we just do the evaluation. We have like policy evaluation with like results like this. Of course, this is as you can see, like this can be quite a bit off, but it's kind of okay. We can just stick with it for the moment. That's the estimate only. But the point is like why we want to do this policy evaluation, as you can see, is like even though like your policies may not be very accurate, or I should say like let me give you an example. Like I guess it will be more can explain better. So let's look at like what we have earlier on, like using value iteration again, like to trying to converge your action. So we start with here something like that. Like this is all the action. This arrows is pointing to actions there. As we do the iteration, you see like this action I change a little bit, like this value is updated like appropriately. So this just repeating what we have earlier on. So, but one thing I want you to this time notice is that like even though my value is still not converged yet, it's not accurate yet, the policy already converged. So therefore, like if you're just interested in the optimum policy, oftentimes you don't actually need to the completely accurate value for your value estimation. So therefore, like what people propose is this policy iteration approach to find the MDP solution is we will stick with like one policy at the beginning, just as we mentioned. I stick with some policy, and then like for this fixed policy, we will try to iterate and get a approximate of the value. With this updated value, we will like do the policy improvement. So now you have this new value, like estimated value. You can update the policy, right? And then like after that, like you just update the value again with the fixed policy. Okay, again, I should emphasize the difference of this approach with the earlier approach is like the earlier approach we always find the maximum, the best action always for each of the iterative steps. Here we'll fix the policy, so therefore like remember this this figure again. The main difference is here. So the earlier approach is always we go for all these different actions in each iteration, but for the later policy iteration approach, we'll fix the policy. Therefore, like it's much less computational intensive. But even doing that, like it kind of converge almost as efficient. Therefore, like typically, like this is a better approach to do this policy iteration. So anyway, both of them, by the way, is just like dynamic programming, really, like to solve the MDP. It's nothing really fancy. Like, so, but now you see like how we can find a good policy or like even the best policy for MDP. Now we can look into the reinforcement learning. So the difference here is like for MDP, we know exactly this transition probability, right? This T as A as pi, right? So we know this model exactly. We know that like, and also we know the reward also, like the reward exactly, like given the state S, given the action, if I reach S pi, what kind of reward I will get. So the thing is like in a kind of like actual environment, like you're not supposed to know exactly what was the reward, right? You have this car, like, okay, so I turn like not quite correctly at this moment. So what was the reward you're supposed to give him? And also like what was the transition probability, by the way? Like if you turn this like 1 degree, like what's the probability that like you move from this state to the next state? And actually, by the way, I think like we still need to define the reward, but the transition probability we do not need, we probably don't know. So so of course, like one very simple way to do it is like you just do statistics, right? You don't know this thing, so you just run it for many times, and then gather the statistics, and then try to approximate this transition probability, right? That would be one way to do that. Another way to do it is using this so-called Q-Learning. Well, actually, let me show you some couple video also. First, like this is showing like how this quite a few years ago, like a decade ago, like using reinforcement learning for control. Like this is like the robot just have a very rough control model, like to teach this, not teach, like control this puppy to walk. And then like this is still, this is still in training, so it's working a bit, quite a bit better. And then after training, it's it's working much better now. So this is also a core example. I may show you later on. It's like, well, actually I may even show you now, maybe. So this is or maybe I should just, okay, I should reduce the delay to make it faster, not increase. So trying to learn to walk. So as the robot here, probably take a while. So eventually kind of moving forward, stuff like that. There's some learning weight and you see there's some epsilon here. I'll explain what is epsilon later on. Learning weight is I just mentioned you need to learning rate is just wait a sec, what's the learning rate now? I'm a little bit, I forgot. So, but anyway, we'll come back to this. Oh, yes. I know why we have the learning rate. I'm thinking because the model is not fixed, of course. So now and there's another main difference doing MDP and also reinforcement learning is for example, you're driving a car I mean this is kind of an offline and online difference. So you want to make sure that you won't. I mean, if you want to drive, you have this self-driving car. You don't want to hit people, at least not very often, right? So maybe every once a year or something like that. Okay, let's go to the. Okay, this actually I mentioned is the model-based learning that is trying to basically just learn this transition probability through statistics, right? So you just do counting, right? So each time you're at state S, take this action with state S pi, you just count how many times you actually get to S1 pi, how many times you get to S2 pi, and so on. Then this, for example, you have 2 out of 10 you get to S1 pi, then therefore S1 pi will be just 0.2, right? So something like that. So after you get the sufficient statistics, then you can just train the MDP as we showed earlier. But it's actually often more convenient to use a model-free approach. That basically, an example would be like this. If I ask you to compute the expected age for a group of students, so one way to do it is probably not the first way that you will think of. Is let's group all these people to have different age and see okay, how many students are actually in age 20, with probability let's say not probability, a fraction 0.35, let's say, and maybe 21 with fraction 0.2 and so on, and then the expected age will be just the weighted sum for that. So that's one way to do it. But a more straightforward way that you will think of is simply counting, right? So you just take all the students' age and then sum of them together and take the average. There's no need to actually build a model the probability model of what's the probability or the fraction of students to have some certain age. So Q-Learning is similar, have a similar flavor. So instead of trying to actually build a model, trying to actually compute this t here, we can just skip this step, skip this step of building this by noticing that as you can see why we are doing Q-Learning instead of V-Learning. So the difference, this is, if you remember this iteration step we have early on for the V. So I'm using this iterative step. We can also write an iterative step for Q here, will become something like that, right? Basically because V is basically just mass of Q, right, over the action. So therefore we will have a Q expression for this one, Q update rule for this one. But what's interesting here, like if you look at this guy here, this is just a probability, this is just a conditional probability, right? And this is like some term here is saying more or less like the QSA is just the average of this term over this probabilistic model, right? So therefore, actually, I don't need this probabilistic model. It's basically just saying that QSA is just the average of all these guys here. Right? It's very similar to I show the example that of average age of students. So in the average age of students, I can either like take the average of all these numbers here, or that will be exactly equal to taking the model of this guy and then okay, let me just, I guess I'm just confusing you like by saying more. Let me just show you like what I have here. So given what we have, therefore we can think of this as simply a sample. So we can think of this as just a sample. And this is nothing, but it's just an average over these samples, right? It's a sample average of this guy here. And then like there's no need to actually build this model here. Instead, we can just simply use a running average, right? For example. So therefore, like we can pick some alpha, let's say. And then like the sample will be basically just this guy, and this will be the previous QSA. And this is like kind of a momentum guy of inertia, as you remember, like in, for example, like in stochastic gradient descent. And that's basically Q-learning. It's actually pretty simple. So therefore, like as you continue to each time, okay, let me repeat, like each time you have a S and A, so now you have this new A pi, right? So you, with this new A pi, therefore you can compute this sample here, then you can just update your Q with this guy here, with this function here, this expression here. And with the Q values, of course, you can now compute the optimum policy, right? But one thing like we are not specifying here, say, let's see. Or like I should say, not specified, but not clearly explain is that like, I mean like, we of course like, each time we can take given this approximate Q assay, we know what's the ultimate action for that one, right? The ultimate action is just maximize A, right? The arc mass of A's will be the ultimate action for that. But the problem is, I remember that like when we first started with the model, this is just an approximation, right? So therefore, like if we just compute the ultimate action based on this, then most likely we'll have like very weird action. So therefore, like there's so-called a term like called exploration versus exploitation. So I think it's in psychology or something like exploitation is like when you use like what you learned already. So that's your QSA model, and actually take the maximum over your QSA, find the arc mass of that QSA. So for the exploration, we'll do something else, basically not using this model here. So at the beginning, as you can imagine, like most of the time we probably try to explore first, right? So and then after a while, like our model is trained pretty well, then we can like move more to the exploitation version. And actually, that's the epsilon we have like when you see the caller robot there. And there's several ways to deal. Okay, this already mentioned that. For the, of course, if you do the exploration, there's also several options, right? Whether you can do it like completely randomly, or actually better yet, you may want to explore to the option that like we haven't explored before. For example, like even we have exploration, let's say if I as current state as I have action A1, A2, and A3, and so on. Maybe I have like do A1 3 times and A2, A3 do 1 times, and A3 did it before. So even though like okay like we decide to do exploration, maybe it makes more sense to explore like stuff that I haven't explored yet, rather than doing like completely randomly. So therefore, in this case, maybe we should favor this action A3 more than the other two. So one way to achieve that is using this exploration function that basically will absorb the this like the number of visits of this action into the objective function. So basically, if you look at this function here, instead of like optimizing this QSA here, now I'm optimizing this F QN here, where n is the number of count for this state S pi and state S pi and A pi there. So then if you look at that here, at the beginning, when this is small, or even like, I think it probably should initialize it to be 1, otherwise it will be kind of like not numerically kind of stable. So, but anyway, when this is initially small, then this will be big value, right? That's more likely like you will explore like this state, or more likely to take the action A pi there. And as this go big, then like, it's less likely to take this action. So okay, regret is we just skip that, but or maybe not. So regret is just a technical term that in reinforcement learning like measure the total number of total mistake cost. So it probably is very important for example, for self-driving car. You want to really minimize the regret. But if you make kind of like kill someone, is like really a mess or something. So and actually what we have previously, this Q-Learning, the problem is that like if you think of like in Q-Learning, we need to specify all this state as A and S pi, and if you have many states, then this would be a very big table here, right? So to avoid that, like, and also like not just is a big table, and some also like very like in lots of applications, it's probably is not a good idea to build this such a big table, because let's revisit this like Pacman example. So we can think of like these different states there, like, but the action of this Pacman should be like rather similar, right? Or like in particular, for example, this case 1 and case 3 here, it's reasonable to think of they are very similar, but you see that the only difference is basically just a dot here is like missing. But we want to kind of so therefore, like, is there any other way to represent this, like without represent like all this possible configuration? So a simple way to think of, okay, I guess I should really let you to think a little bit like what is the possibility to reduce the number of configurations here? So instead of like kind of like coding all these possible states and configurations, like what are some possible alternatives?
class, we considered doing something like this with all the states, but instead we made a sort of value function with a bunch of constants. So instead of learning each state, we just learned the constants. So just try to do that. But,
So what are the constants?
Well, in this case, like in the game, so you have like a distance from like how much energy the ship has.
Oh yes, exactly, precisely. I'm looking for this your answer. Yes.
Yeah.
So
then we're like, so we just combine them all into one equation. And so we just have
yes.
the constant.
What are the names of these constants? Like, yeah, actually, yeah, you're completely right. So what you mean by constants are the features, right? So it's like connect to all other machine learning methods, like supervised and unsupervised. We kind of like from the data we first like transform this input into like some set of features, and then we can process those features instead of like process that input like directly. So is that
Kind of what we did.
is that?
Ours was simpler though. It was just like,
Yeah.
so we just put it into an equation and just,
Yeah.
this was like those three values we had that were, and we just multiplied it by a random number. And we learned those random numbers.
Okay, I guess like what we're going to talk about is similar to what you have, except this is exactly the same, right? So this is the features, like you mean the constant or something like.
Yeah.
So you instead of like have all these possible states, so we probably just extract features here, like maybe like just the distance to the closest goals and like closest start and so on and so forth. But by the way, like you said, like your kind of a project, or like what was that like? You mentioned?
This was for artificial intelligence, but yeah, it was a project.
Ah, okay. So it's a CS course?
Yes.
Okay. It's a game programming, like what is that?
Yeah, kind of. So she gives us a very basic game where it's just you have a ship and it's gathering resources.
Yeah. Is that Amy teach that?
Yes.
Oh, okay. Yeah. So yeah, that's exactly like you have this is basically the features, right? And now instead of like have this Q stay here, so we have these features to represent those states instead. So more precisely, like you can think of like these features are the basis, and the Q state is just a linear combination of these features. So and then like the value function will be also like that. Like value function is like just also the linear combination. I actually this probably should have a different notation. Like this shouldn't be the same function here. And then basically, so if we want to learn it, it's like just going through the more or less the same thing there. So remember, like in the previous Q-learning, we are trying to learn basically like Q with some sample is like constructed from here, like from this guy here. Now our Q now is like constructed by this guy, right? So I will have the difference is that, but also like because my parameter now is like this W instead of like Q here. So my gradient is like I need to, instead of like partial this cos partial Q, so I have like partial cos partial W I, right? But this is like partial cos partial Q partial W I. So therefore, like if I do partial Q partial W I have this. I have Fi here, so therefore I also have Fi term here that I need to add that. So an intuitive explanation and interpretation to have this Fi, you can also think of like you should, if something bad actually happened, then you should also only bring the features that is actually turned on, right? The features is actually activated. So therefore, yeah, kind of makes sense. So I don't know whether I should continue with this. I guess I probably will continue next time, and then I'll just stop here. So.